Okay, today we're going to finish up our foldable and looking at the remaining two examples of how we can work with inverses. Last time we did a little bit of review of our chapter 6, simply evaluating our trig functions for given angles. We looked at how that then connects with our inverses, which was working backwards. We looked at some composition with our inverses, thinking about where we found the inverse, whether it was on the inside or the outside. But the key on these ones last time is that each time these two trig functions were the same. So remember, you can view these as the idea that if the trig functions are the same, then the functions themselves cancel out and you simply do an analysis of the ratio. Or here again, if the trig functions are the same, they would cancel each other out, and we did an analysis of our angle this time. Today what we're going to do is we're going to look at our composition of our inverses and our trig functions, but this time we're going to have different trig functions. So the function that's on the inside will be different than the function that's on the outside. These problems aren't much different than what we've done before if we look at them in terms of pieces. If we come back up here to our top windows and we call a simple evaluating of an angle, if I call this an A problem, okay, I'm going to refer that to as an A problem. So evaluating a trig function for an angle, if I come down here, I can see that this inner function here would represent an A problem. And if I look over here, I'll actually end up with an A problem as well. So in just a moment, I'll come back to this idea. On this one, evaluating our trig functions, that's just simply working backwards from these, we can call that a B problem. So now if I come down here, I can see that my inner function is a B problem. The only difference between these is that the A and the B flip. So on this problem, the inner function is an A problem, but after we solve that, it turns into a B problem. And on this one, my inner function is a B problem, and then after we evaluate that one, it will actually turn into an A problem. So as long as you think of these as A-B problems, deciding your order, they're really not a big deal. So let's just start with the windows. So let's start with our right window here, evaluating A's on the inside, a B's on the outside. Okay. So when I think about these, what I want to remember is that first of all, we are going to want to work inside out. So we're going to work inside out. So we're going to work our A problem first, and then when we're all finished, our final answer will be an angle. So you should give some kind of an angle when you're all done. So the A problem first, the cosine of pi. Thinking about our unit circle, we know that the cosine of pi is going to be the y coordinate. So, or the x coordinate, apologize for that. So we're going to do the cosine of pi. We're going to look for the x coordinate at pi. Sometimes people like to even kind of give yourself a mental of what that x coordinate would be. So this inner piece turns into a -1. I still have this outer piece, which is the inverse tangent of -1. So now I had an angle to begin with, and now this inner piece, I understand because I'm working with an inverse, is now actually a ratio. So what I'm asking myself is, what location within my restricted quadrants is tangent a -1? So it's always helpful, again, to identify what your restrictions are. So we know tangent can't appear in either of those quadrants. So of my remaining quadrants, if you still want, you can write the all students take calculus. I know tangent would be -1 in this last quadrant. I know that the angle would be normally positive rotation would be 3 pi over 4. But of course, in that fourth quadrant, I must do the negative coterminal angle. So my final answer is a -pi over 4. And hopefully you can see there that it was simply evaluate an angle and then rewrite the problem. So we can do a couple more examples here. Again, we can work with our inner function first. Cosine of pi over 6. Again, cosine is going to be my x-coordinate at pi over 6. So that piece is going to give me a square root of 3 over 2. Bring down your inverse function. So now I have inverse sine of square root of 3 over 2. If you want, you can identify your restrictions again. Never hurts. Doesn't take very long to do. So what angle is cosine or is inverse sine square root of 3 over 2? I know it has to be in the first quadrant because I'm working with a positive ratio, and my angle would have to be pi over 3. Just thinking about that unit circle. Moving on, inside piece, tangent of pi over 4 is of course going to be a 1. Now I'm going to do inverse sine of a 1. So where is my y coordinate on my unit circle of 1? That's going to happen at pi over 2. So you can see how important understanding our unit circle was for us. Again, if I wanted to do my restrictions, my pi over 2 lands right there, and I need to remember that that point is included in the accepted interval for inverse sine. Continuing on, sine of 11 pi over 6, evaluating that angle on my unit circle. We certainly can evaluate the angle and picture where it lands if you need. So 11 pi over 6 would put me in that last quadrant there. Sine of 11 pi over 6, I know my answer is going to be negative in that last quadrant, so I have a negative 1/2. Now I'm going to do inverse cosine of that. So now I'm going to think about my cosine restrictions. Cosine restricts and is not allowed in those two quadrants. So all students take calculus tells me that cosine is going to be negative in this quadrant. I know cosine is a negative 1/2 in that quadrant when I'm looking at the angle 2 pi over 3. Okay. The last side, we can make this a little extra long video today. My last side here, we're just going to work the other direction. Now this first one is a little bit different. We simply in that when I look at this value here, understanding that this is a ratio, I understand that this is a ratio, and this is not one of my special angles. So the first thing that I'm going to do there is I am actually going to give myself a little triangle. So I'm looking at inverse sine, so I'm going to put my restrictions on here. I see that it's negative, so I'm going to draw my triangle, remembering the right angle has to be on the x-axis. I know that sine is opposite over hypotenuse, so I can put my 10 on the hypotenuse, I can put my 7 on the opposite, making it negative. I can do a quick Pythagorean theorem mentally or actually writing it down. My 100 equals 49 plus x squared, which is of course going to give me a square root of 51 for that x value. Now, if I want, I can simply look at this cotangent here, and what I'm asked to do is evaluate cotangent at this location. So I just need to evaluate cotangent of that triangle. So cotangent, if I'm thinking SOHCAHTOA, I'm going to do adjacent over my opposite. So my adjacent I can now see is a square root of 51. And my opposite, of course, is this negative 7. Now this one's a little bit unique just in that it's not a special angle. But just like we said earlier, this inside piece is going to be a B problem, and then we'll do an A problem after that. it's important to remember that your final answer on these problems is a ratio, because the last thing we're going to do is evaluate an angle and get a ratio, and that makes sense for us, the type of answer we got right here. So my last one here, when I take a look at this inverse sine, I always like to mark those restrictions. Where is inverse sine of 0? Where does inverse sine equal 0? So I'm looking for what angle would give me a ratio of 0. I know that that's actually at an angle of 0 radians. It can often be confusing for students because this was a ratio, but this is an angle. So now I can rewrite the problem if I want. I need to evaluate secant of 0 radians. And I know that secant is going to be 1 over the x-coordinate at that same location. Probably know it in our head, but because this is sometimes a confusing location, I'm going to write that one for you, 1, 0. So I simply have 1 over 1 or just 1. Moving on, I'm going to do my inverse secant of 2. And again, I want to think about what are my restrictions for inverse secant. Remember, we're going to eliminate these 2 quadrants. It's also important to remember that I cannot include the value at pi over 2 because on our graph we would have an asymptote there. So now, where is my inverse secant a 2? So if you're picturing in your head, we're really thinking the reciprocal of 1/2. So of my values here, I'm here in this first quadrant, and I'm looking at a pi over 3. So I can rewrite this problem as sine of pi over 3, and now it looks like one of my A problems, and my answer is radical 3 over 2. Moving on, my last example for today, inverse cosine of 0. I like to put my restrictions on there. I want to know where my x-coordinate is 0 for cosine. That's going to be up here on the top. It's allowed for cosine, not for secant. So my x-coordinate is going to be there at pi over 2, so I'm going to do cotangent of pi over 2. I know that cotangent I can think of as slope, so instead of thinking the slope of the y-axis, it's cotangent. I'm going to do slope of the x-axis, so my answer will be 0. And that's all we have for inverses.